we're going to look at a required practical, and this is measuring the rate of reaction by an initial rates method. And so we're going to look at the reaction of iodide ions with hydrogen peroxide in acidic solution. And this is also known as the iodine clock experiment. So I'm just going to run through the method quickly. So first you use a pipette to transfer 10 centimeters cubed of hydrogen peroxide solution to a beaker. And then you use a measuring cylinder to transfer 25 centimeters cubed of sulfuric acid into the same beaker. And then using a burette, we measure 20 centimeters cubed of distilled water into a bigger beaker, so 250 centimeters cubed. And then we add a centimeters cubed of starch to this beaker, and then 5 centimeters cubed of sodium thiosulfate solution. We then stir the mixture and pour in the hydrogen peroxide sulfuric acid mixture and immediately start the timer. We then stir the mixture and stop timing when the mixture turns blue-black. And we repeat these steps, but with different volumes of the water and potassium iodide solution. So what's actually happening here is that the hydrogen peroxide reacts with the iodide ions to form iodine and thiosulfate ion. And we write this in the equation like this. So this is hydrogen peroxide, and this reacts with the iodide ions to form iodine and water. And then what happens is that the thiosulfate ion then immediately reacts with this iodine which has been formed. And so we have this second equation of this thiosulfate ion reacting with this iodine that's been formed by the first equation to form two iodide ions and this S4O6 2- ion. And so when the iodine is produced, has reacted with all of the thiosulfate ions present, excess iodine remains, and this remains in the solution. So then reaction with starch then forms the dark blue colour that we see. So if we vary the concentration of I-, we can determine the order of reaction with respect to I- ions. So the rate equation for this reaction is actually like this. So you have rate, and it's equal to K multiplied by the concentration of I- to the power of M, and then multiplied by the concentration of the hydrogen peroxide multiplied by N. And so by varying the concentration of the iodide ion, we can determine its order, M. And the order with respect to iodide ions is found by varying its concentration whilst keeping everything else constant. So the rate equation therefore simplifies to rate equals K multiplied by I- to the power of M. Or we can take logs, and this will make graphing it a bit easier. So we could have the log of the rate is equal to M times by the log of this concentration I plus a constant. So then now we can plot a graph of this. So if we say this is Y, and then we have X plus C, so that means that we're plotting a graph of log rate over log of the concentration of I-. And so this M here, this will be the gradient, and this will also give us what the order with respect to I- ions is. And the way we plot log of the rate is if we do log over 1 over the time, because rate is equal to 1 over time. So we plot log over 1 over time as the y-axis, and on the x-axis, the total volume of each of the solution in each experiment is constant. So the concentration of I- can be represented by the volume of the potassium iodide solution. And so we plot log of the volume of potassium iodide on this x-axis. And what we should get is an order of 1. So the actual rate equation is rate equals K multiplied by the concentration of I minus to the power of 1. So we should get a straight line graph.